Hello, and welcome to this SPHN tutorial entitled Querying Data with SPARQL. This tutorial aims to give an overview of SPARQL as querying language of data that is being annotated in the SPHN context. My name is Vasundra Touré, and I am a scientific coordinator in the Personalized Health Informatics group at the SIB Swiss Institute of Bioinformatics. We will first introduce SPARQL 1.1 as a querying language before diving into concrete examples where we will be interested in patients' data having allergies to specific substances or that are being annotated with certain types of lab tests. Let's begin with the introduction to SPARQL. SPARQL stands for SPARQL Protocol and RDF Query Language. It is a standard that is used for querying any data that is encoded in RDF, and it is a declarative type of language that is part of the W3C standards. More information can be found in this documentation. The queries that are built in SPARQL are based on a graph pattern matching finding, meaning that the tool that is doing the search will try to match the given pattern in the query and retrieve data that corresponds and actually fits to it. In the example below, you can observe a triple, which represents a resource, hospital A, which has a relation, has subject pseudo-identifier, to a patient. This is a valid pattern that can be looked for in the SPHN project. And if you look closely, the patient has a question mark in front. The question mark is one of the syntax that is being used to refer to a variable of interest in SPARQL. In this example, the query would simply be retrieving information about which patients have been registered or went to hospital A, or in other words, from hospital A, give me the list of patients. So in this tutorial, we will gradually see how queries are being built, but one thing you may notice is that the syntax is quite similar to the turtle format, but it is not exactly the same. The structure of a query is deconstructed into different parts, some of which are mandatory and represented in bold here, and other are optional. First, it is possible to declare prefixes that can be used later on in the query for simplifying the query writing and the visual overload. Then it is necessary to declare the type of query. There are 4 types that are available, and we will see in the next slide what they do. Then it is also possible to declare some dataset, so from which dataset the query must be ran against using the statement from or from named. And the from named means that you can use it in case you have encoded your RDF graphs into named graphs. Then there is a mandatory statement where, which must be provided. It contains the graph pattern depicted as triples, which constitute basically the core element of the query. It enables to define in which part of the graph the triple store should match and retrieve the wanted results. And finally, it is possible to define query modifiers in order to present the results in a specific way. So for example, you can either order the results by some criteria, or you can also group them to aggregate some information and so on. So now the 4 types of queries that are possible are the following. You can first make a select statement where you would get the results for some requested variables, and the output that you have from this type of query would be a table that you can then process further if you would like. Then the second type of query would be the ask statement, which checks for matches of a given query and retrieves a boolean of yes or no answer. So this is the result that you will get. The construct type of query retrieves specific parts of a graph, but it also enables you to manipulate the graph by creating additional triples that you would like to add into your data. And finally, the describe outputs basic information about a given variable. meaning that if it would provide you all the metadata that is connected to it. There are also other query formations that are possible, like the nested queries or the federated SPARQL, but we will not go into details in these constructs in this beginning tutorial. So you are welcome to check the documents that are being linked here in case you would like to know more about these. Before we get to our examples, there are a few tips to keep in mind. A is a shortcut for the RDF column type, meaning that if you write RDF column type or if you write A, it will be understood the same way by any triple store. It is also highly recommended to define and use prefixes for having a better readability of your query. And also one important point is to be familiar with the structure of the dataset that you are querying. This tremendously helps the process of writing a query for getting the data of interest or just simply doing a particular data analysis for a specific study. When one person is not familiar with the dataset, it can be difficult to know which element is connected to which, or even what is the exact name of that connection. So I would really recommend you to get to know about the way your dataset is actually structured. The schema provided, to which the dataset complies to, can usually be used for this purpose. So now let's move to our second part of the presentation, which is about the query examples. Before we go into the query details, it is good to have an overview of the structure of the data that we are interested in. Here our question is, which patients are actually allergic to the peanuts? And in order to assess that, we have an extract of the SPHN RDF schema here, which represents the pattern of data that we are interested in order to respond to this question. So we first have an allergy episode class, which represents the episode of allergy that a patient went through at some point. And this allergy episode is connected through the property has subject pseudo identifier to a subject pseudo identifier class, which is basically information about the patient. In addition, the allergy episode has a has substance property, so it is connected to a substance class, and this substance is further connected to a SNOMED CT code that refers to peanuts through the has substance code property. So this is basically the pattern that we are interested in querying in our data in order to get all the patients that are allergic to the peanuts. So how do we do that? We first need to define our prefixes, as we mentioned before. So we have some generic prefixes from RDF, RDFS. We have some internal defined prefixes like SPHN or the resource or SNOMED CT. Then we need to write our type of query, which here is a select, and we are interested in getting distinct patients. So patient here is our variable of interest. And this is what we will get as a result. Then we are writing our graph pattern with the statement where. So we are first stating that our patient must be of type SPHN subject pseudo identifier. This is represented with this red arrow here, that there must be this connection between this variable of interest and the subject pseudo identifier. Then we are defining a variable allergy episode for representing the allergy episode from SPHN. So there must be an allergy episode which is of type SPHN allergy episode. Then similarly we have a substance variable which refers to an SPHN substance. And then we need to link all these variables together in order to get the data that is actually connected here. So we first need to say, okay, the allergy episode variable must be connected to the patient through the has subject pseudo identifier. The allergy episode must also be connected to the substance through the has substance. And finally, the substance had a further annotation through the substance code. So we are also representing this. So the substance variable must be connected to the substance code through the has substance code property. And this substance code must be of type this SNOMED CT ID, which corresponds to peanuts. And there we have our full pattern of interest, and the triple store in which you're providing this query will query for this pattern, try to find any data, so any patient that actually fits to all these patterns. And you will get a list of results, a list of patients that are actually matching this graph. So now that we have written down our full query, we are able to put it on a given triple store and run it to see what results we get. So we did that with the GraphDB triple store, the free version. So we have already imported some mock data in there. If you would like to know more information on how to import data into GraphDB and explore the content of it, I would like to invite you to watch the video that appears now on the screen. For this tutorial, we are interested in running queries. So we go to the SPARQL tab here. We can create new empty tabs where we can add and copy paste our query. But we have already prepared, for the sake of the tutorial, the queries that we will be running. So here we copy pasted the query that we just developed in the tutorial, and we can run it, and we see at the bottom the list of patients that are allergic to peanuts. If we want to get the count of the amount of patients that are allergic to peanuts, you can write down this query where you have the specific count of patients which are grouped together. Followed here, we added the SNOMED CT code and its label. This query needed to be updated with the following information here. So stating that the substance code is this SNOMED CT code, and we wanted to have the label connected to it. So we are exporting from this SNOMED code the label. So if we run this query, we can see that we have 134 patients that are annotated to be allergic to the peanut substance. So if we go back to our presentation, this is the result that we obtained for this query. But we may be interested in other type of allergies. So now we are interested in patients that are allergic to pulse vegetable. What is the pulse vegetable? It's a family of elements that group bean sprouts, lentils, beans, peanuts, and you have different levels of hierarchy here that is represented in SNOMED CT, meaning that if you want to get patients that are allergic to pulse vegetable or to any type of pulse vegetable, it would be more accurate to get patients that are annotated to be allergic to pulse vegetable, but also to bean sprouts, to peanuts, to salted peanuts, and all the elements that are children of the pulse vegetable. So you may note that patients can actually have different levels of granularity being annotated. And if you want to query for patients that are allergic to any type of pulse vegetable, you do not need to query individually for all the levels in order to get all the patients that are of interest. But thanks to the graph structure provided with RDF, and especially with the hierarchical structure from SNOMED CT, we can do this query in a more straightforward way. So there are two options to query the patients that are allergic to any type of pulse vegetable. One is to reason with the query, and in this case, we do not have any inference turned on. We will see what this means later. So in order to query for patients that are allergic to any type of pulse vegetable, we have the same sort of schema from our graph pattern to begin with. So we have our patient, we have an allergy episode connected to a substance, and this is where the change occurs. So we have a substance code, but now instead of saying that we are only interested in patients that are allergic to peanuts, we need to state that the patient can be allergic to anything from the pulse vegetable level and all the inner components. And you can do that by specifying that we have a variable, pulse vegetable and descendant, and this variable should be a subclass of pulse vegetable. So this is the code for the pulse vegetable. And in order to state that we want to get all the nested levels from pulse vegetable, and not only bean sprouts and peanut, but also the salted peanut and the peanut butter, we need to put this asterisk in behind after the subclass of. So by doing that, it goes into the different levels of from pulse vegetable and all the nested ones. So now if we put that query in our GraphDB instance, we can run it and we again get a list of patients. But the most interesting part would be when we are grouping the SNOMED CT codes annotated and the number of patients that are allergic. If we run it, you can see that there are 123 patients that are being annotated as allergic to bean sprouts, 123 again annotated as being allergic to pulse vegetables, so they have not been specifically annotated for a specific type of pulse vegetable. And then we have 134 patients that are allergic to peanuts. This is what we observed in our query before. So this is one option to query for nested levels of information. So we have the results here that states that we have 133 patients allergic to peanuts, 123 to pulse vegetable, and 123 to bean sprouts. And there is a second option where we can turn on some inference. You can do this by going to the setup, my settings, and turn on the inference. There's also another option to do it for a specific query. We will see that soon. But first, what is inference? In RDF, there is this component called reasoning, which enables you to give the possibility to the computer to infer knowledge based on information that is provided to him. So the ontology here is a key element for this reasoning purpose. So you have possibilities in ontologies to define hierarchies with classes and subclasses. So here we have a measurement under which we have a heart rate and a body height. So body height is a type of measurement and heart rate is also a type of measurement. But we also have the same with properties and subproperties, where we can define hierarchies in the way we define properties. Then we have some data that tells us that X is a heart rate, or for example, that X has an insertion site arm. With RDF, the computer is able to do some reasoning. So there are some reasoning that tells you that when there is a hierarchy given in the classes or the properties, you can infer some type of knowledge. So given that X is a heart rate, the computer is able to reason that X is also a type of measurement, because we know that heart rate is a type of measurement. So if X is a heart rate, X is also a measurement. Similarly, for the properties, X has an insertion site arm. It means that X also has a body site arm. So that way the computer sort of do some reasoning, inferences of knowledge based on information that is being provided to it by the ontology, and knowing what the data is telling them. So we can use this reasoning possibility and simplify our query to get patients that are allergic to any type of pulse vegetable by simply stating that we are interested in an allergy episode where the substance code is this pulse vegetable code. And we do not need to use the RDFS subclass of that we used previously to state, okay, you need to go into all the levels. So when we turn on the inference, we can see that you can turn on, we saw that we could turn on the inference in the setup, but you can also go to the query that you want to run, and you have here this arrow that enables you to turn on inference data. So you can click on it. Now the inference is turned on, and if I run my queries, I again get a certain amount of patients. So you can see that I did not need to tell the query that I need to go into all the subclasses of the pulse vegetable ID. And if we make it as with counts, we can run our query with inference turned on here. And you can observe that we get more results than before, but more specifically, we can see that we have 134 patients that are allergic to peanuts. We have 123 patients allergic to bean sprouts. But more specifically, when you look at the pulse vegetable, we get the list of 380 patients. So this is the correct, more accurate statement saying that 380 patients are allergic to any pulse vegetable, any type of pulse vegetable. So this is how the inference works. You do not need to specify, go into all the subclasses. You simply state the code that you're interested in, and then with the inference on, it looks into all the levels. So you can see now in the results that we have 134 patients allergic to peanuts, 123 patients allergic to bean sprouts, but we have 380 patients that are allergic to any type of pulse vegetable. Now we go to another type of query that we can do. So we are interested now in patients with measurements of leukocyte in blood by automated count. So this is a specific LOINC code that gives results about patients that had a lab test done specifically for leukocyte count in blood. So again, as we did before, we need to inquire what is the data or what is the pattern that we are interested in our data. So we have a lab result class that is connected to the subject pseudo-identifier through the has subject pseudo-identifier property. And we also have a lab result test code that is provided with the LOINC code that is connected to the lab results through the has lab result lab test code. So this is the pattern that we're interested in. This results in the following query where we have our prefixes defined. We have our patient initially, which is a subject pseudo-identifier. There is a lab result variable that we defined, which is of type lab result. And we have a test code, which is this specific LOINC 6690-2. And if we run this query into the GraphDB, this is what we observe. So we have a list of 253 patients. And if we get the count here, this is also what we get. We have 253 patients annotated with having a lab test code of leukocyte in blood by automated count. Now what we can do also is to go one layer up, and maybe we don't know which LOINC code we want to retrieve, but what we are interested in is we are interested in patients that had measurements done of leukocyte in blood. So LOINC has specific annotations given to the different codes where we have the has component and has system. So in the LOINC RDF schema, we have a property has component that links to a component, and we also have a property has system that links to blood in this case. And how do we query that? So that you can see that this is our pattern of interest. If we want to query for this, we have to state that now the code is not a specific LOINC code that we know about, but it is a variable where we need to have the property has component linked to a leukocyte. So this is how we write it in the query. And we also need another component, another property linked from this variable to BLD, so blood. And this is how we write it. So it is through the has system property. And now if we go back to our GraphDB, we can run the query. We get, again, a list of patients, but if we get the counts of these patients that have been measured with leukocytes in blood, you can observe that we have two different codes that results. So we have 247 patients that were annotated with having a test done, which was measuring leukocytes in blood, and 253 patients had a test done, which was measuring leukocytes in blood, but by automated count. So these are the subtle differences in the coding systems that you can have, where many codes can be used for similar things, but still with a slight difference. And if you're not interested in having the only the patients with automated count, and you want to know all patients that got leukocyte in blood tested, this is the type of query that you need to. It would be more interesting to do this type of query. So depending on the research question that one may have, it is important to think carefully about the query to build in order to get the most accurate result. You have seen in this tutorial a few possibilities for querying data based on the way schemas are built. And in the context of the SPHN projects, the graph structure can help in acquiring these results with maybe a bit less efforts thanks to the reasoning possibilities that are provided with the RDF framework, but also when we actually know how to write these queries and when we know about the structure of the data. So these are some references that you can go through to get to know more about how SPARQL queries can be built. We also have some more documentation in our SPHN semantic framework, read the docs. And if you're interested in the external terminologies, LOINC and SNOMED CT that we presented in this talk, you are welcome to read our documentation. Thank you for your attention, and if you have any question, do not hesitate to drop us an email.